Welcome back. So in our last explainer, we looked at the half-wave rectifier. And yeah, it's a great starting point, but it has this one massive flaw, right? It just throws away half of the AC power cycle. Today, we're going to dive into its much more capable sibling, the full-wave rectifier. These circuits are the absolute workhorses of power conversion, and they really do form the backbone of countless industrial applications.
All right, so here's our game plan for today. First, we're going to start with the why. You know, the basic problem that full-wave rectifiers were invented to solve. Then, we'll get into the how and explore the two classic designs engineers use. From there, we'll see how you take that bumpy output and turn it into pure, smooth DC. Then, things get really interesting. We'll uncover the magic of how you can actually make power flow backward. And finally, we'll see what happens when we take all these ideas and scale them up to an industrial level.
So let's kick things off with the fundamental problem here. A simple half-wave rectifier, it just chops off the entire bottom half of the AC wave. I mean, sure, that technically gives you DC power, but it's incredibly wasteful. And as we're about to see, it can cause some really serious problems for whatever power source it's connected to.
This slide just nails the core upgrade. On the left, with a half-wave, you're literally throwing away 50% of the available energy. But it's actually worse than just being inefficient. That unbalanced DC current, it acts like a permanent magnet on the iron core of a transformer. It can saturate it, causing it to get incredibly hot and stop working properly. The full-wave rectifier on the right, though, that's the elegant solution. It cleverly flips that negative half of the wave up, which means we can use the entire cycle. Not only does this double our power, but it also keeps the current perfectly balanced, which protects our equipment.
Okay, so now that we get why we need to use the full AC wave, the next question is, how do we actually do it? Well, engineers have come up with two main ways to build these circuits, and as you'll see, picking between them is a classic engineering trade-off.
This table lays out that trade-off perfectly. The bridge rectifier, yeah, it uses 4 diodes, but its big advantage is that it works with any old standard transformer, which makes it super versatile. Now the center tap design looks simpler, only 2 diodes, but it needs a special and usually more expensive transformer. But you know what? The third row, that's the real deal breaker in a lot of cases. Look at that peak diode voltage. In the center tapped circuit, the diodes have to be able to handle twice the peak voltage. Now for high voltage systems, that is a huge problem, and it's a major reason why the bridge rectifier is the go-to choice for so many applications.
And here's a really key takeaway from all this. No matter which of those 2 designs we use, the result is an output ripple that happens at twice the frequency of our AC source. So if you've got a 60 Hz input from the wall, you get a 120 Hz ripple coming out. Now this might sound like a small detail, but trust me, it's a massive advantage. Why? Well, because a higher frequency ripple is way easier to smooth out, which leads us right into our next section.
So, that pulsating DC we just made is okay for simple stuff, like charging a car battery, but for our computers, our servers, or pretty much any sensitive electronics, it's totally unusable. We need a smooth, stable, constant DC voltage. So, let's figure out how we filter out those bumps.
Now, to really tackle this ripple, we can use this powerful math tool called the Fourier series. The basic idea is that any complex wave, like our bumpy DC, can be broken down into a mix of simple, pure sine waves. And what this quote tells us is that our wave is basically made of 2 things: the pure DC voltage we actually want, plus a bunch of unwanted AC ripple frequencies we call harmonics. And because of the nice symmetrical way our full-wave rectifier works, these harmonics only pop up at these predictable, even multiples of the input frequency. This is fantastic news for engineers, because it means we know exactly which frequencies our filter needs to get rid of.
So the simplest way to filter this is to just put a big capacitor right across our load. Think of it like a small water tower. As the pulsating voltage rises up to its peak, the capacitor fills up with charge. Then, as the input voltage starts to fall back down, the diodes shut off and our capacitor acts like a reservoir. It slowly releases its stored energy to the load. This whole process just smooths out the dips and gives us a much more stable DC voltage.
But there's a catch. This simple capacitor filter has a pretty big flaw. To top itself up with charge, the capacitor yanks a huge amount of current in a very short, very intense burst right at the peak of each wave. These repeated current spikes put a massive amount of stress on the diodes and on the transformer. For, low-powered gadgets, maybe it's fine, but for anything serious, this is an inefficient and potentially damaging way to do things.
And this slide shows us a much more elegant solution. By adding an inductor, which is basically just a coil of wire, in series with the load, we can solve that current spike problem.
See, inductors, just by their nature, they resist sudden changes in current. So the inductor acts like a shock absorber for the current, while the capacitor is still acting as that reservoir for the voltage. Together, this LC filter gives us smooth current and smooth voltage. It's really the best of both worlds. But even this advanced filter isn't perfect. It has this kind of weird behavior when you have a very light load, when not much power is actually being used. If the load current gets too low, the energy stored in the inductor can completely run out in between those pulses. This is what we call discontinuous mode, and when that happens, the output voltage is no longer being controlled by the filter, and it can unexpectedly shoot way up towards the peak input voltage. That is a critical detail that designers have to plan for to avoid frying the equipment.
Okay, now things are about to get really, really interesting. So far, everything we've built is basically a one-way street for power. But what if we could do more? What if we could install a traffic light to precisely control the flow? Or what if we could do something that sounds like it breaks the rules of physics? Make the traffic flow backward, from the DC side all the way back to the AC source. To get that kind of control, we need an upgrade. We swap out our simple diodes for something called a thyristor, or an SCR. The easiest way to think about it is like a diode that has a security guard at a gate. It still only lets current flow in one direction, but it will stay completely closed until it gets a tiny little electrical go signal. By controlling the exact timing of that signal, we can decide the precise moment in the AC cycle that the thyristor turns on, and that is the key that unlocks a whole new level of control.
So this brings us to a really fascinating question. We've built a rectifier, a device that's designed to send power in one direction. But with these new controllable thyristors, can we actually reverse that flow? It seems like it violates the entire purpose of the circuit, but with some clever timing, we can pull off one of the most remarkable tricks in all of power electronics.
The secret is all about when we send that go signal. If we intentionally delay it and wait until we're past the peak of the AC wave, specifically past that 90-degree point, something incredible happens. The average output voltage of our circuit actually becomes negative. Now remember, the thyristors are still one-way gates, so the current can only flow in its original direction. It stays positive. But think back to your basic physics. Power equals voltage times current. So now we have a negative voltage multiplied by a positive current. The result? Negative power.
And what on earth does negative power mean? It means power is flowing out of the DC side, maybe from a huge battery bank or from the regenerative braking system on an electric train, and it's flowing back into the AC grid. Our circuit has completely flipped its job. It's not a rectifier anymore, it has become an inverter. And this isn't just a cool party trick, it's the fundamental principle that allows those massive high-voltage DC transmission lines to efficiently shuttle power across entire continents.
Now let's take everything we've learned and scale it way up to the kind of massive power levels you see in factories, data centers, and heavy industry. For these kinds of jobs, we don't use the single-phase power from a wall outlet, we use three-phase power. And at this scale, we have to face a real-world limitation that our perfect ideal models just ignore.
This slide shows you the huge advantage of three-phase power right away. Instead of just one sine wave, we have three of them, all working together. After we rectify them, our output isn't made of 2 pulses per cycle, it's made of 6. This creates a DC output that's naturally much smoother from the very beginning. And just look at the chart. The first big ripple frequency we have to filter out is way up at 6 times the source frequency. That makes it incredibly easy to filter, which means smaller, lighter, and cheaper filter parts. For any industrial scale project, that is a massive win.
And now for that reality check. This right here is one of the fundamental rules of electricity and magnetism. Every real-world AC source, whether it's the power grid or a local generator, has some amount of inductance, just in its own wiring. And this simple fact of physics creates a complication that every single high-power circuit designer has to deal with.
So this slide shows us what that real-world problem looks like. Because of that inductance in the source, the current can't just teleport instantly from one diode to the next. Instead, there's this brief but very important overlap period where 2 diodes are actually conducting at the same time. We call this commutation. And for that tiny moment, the AC source is basically short-circuited through those 2 diodes. This carves a little notch out of our output voltage. And the more current the load is pulling, the longer this overlap lasts, and the bigger that notch gets. This causes the average DC voltage to sag, an effect that every high-power design has to account for.
So,
We have covered a ton of ground, all the way from the simple idea of just flipping a sine wave to the complexities of power inversion and industrial commutation. It's pretty amazing to think that these principles, some of them over 100 years old, are the very foundation of our modern world, from EV chargers to the smart grid. And that brings us back to the big question here. How are we going to keep using and innovating on these core ideas to build our future?
If this explainer helped you get a better handle on these concepts, taking just a second to subscribe and hit that like button is honestly the best way to support what we do here. It tells the platform that this is valuable content, and that lets us create more deep dives into complex topics just like this one.
And now, I want to hear from you. Seriously, I read every single comment. Did that whole commutation thing spark your curiosity? Would you like a dedicated explainer where we dive into the math of calculating that overlap angle? Or maybe you're interested in something else entirely. Let me know in the comments what you want to see next. Thank you so much for watching.